lots of times with science, some scientists are so humble. Like there's people like Michelle Thaler and like Brian Cox. Like they'll talk to you. They'll actually speak to you like a human being. They won't try to like just sound so smart and use big words and like you can't catch on to like what they're talking about. But then there are some other guys who I believe they think they're like in the elites or whatever, perhaps certain mathematicians. And, they don't really, not so inclusive, with this kind of thing. And I think the average person really wants to know about this stuff. So what I was going to talk about today is a couple little simple things. This is going to change how you look at motion, displacement, curvature, general relativity. Quantum mechanics has everything to do with general relativity. Just even take the vacuum of space, like you've heard of the Big Bang. Okay, well, what was the Big Bang? Well, we know space is full of fields. So even empty space is full of fields. Like the electron, that's an electron field. So you'll either have energy coming in or energy going out, but it's a field. Most of the mass, 1% mass comes from the Higgs. The reason why is because when you think about quarks, in triplets moving around at almost light speed, when they have to move through the Higgs field, that slows them down a little bit. And that little bit of an inertia created there is that 1% rest mass. That's what gives you the hook. I call it the hook, to begin to get other excitations, other wavelengths to catch on and to start to build something you or I would call a particle. But basically, we'll just start with up and down quarks. With protons and neutrons, you have charge. Okay, so with a proton, you got a positive charge. It also has a mass. With an electron, you got a negative charge. It also has mass, but it's a very little bit of mass. The proton has most of the mass, and most of the mass comes from the strong nuclear force. It's that little tug of war or wrestling match between the gluon and the quark. That's what gives you most of the mass of your nucleon. And your nucleon is what builds a hadron, and then so on and so forth, all the way up to an atom and then a molecule. So you start off with these three quarks. You'll either have two down and a up or two up and a down, okay? And they have charges, and that's inside your proton and neutron, and like for instance, just take hydrogen. Hydrogen just has one proton, right, and one electron. You move up, you get into helium, now you have a proton, neutron, and two electrons. And that's how the atomic numbers go all the way up to and including when you get into metals that are born in star remnants and neutron stars and things like that. But basically, this nucleon is what gives you the basis, but it all starts because of that vacuum value, that VeV, vacuum expectation value, which basically just tells you that like even empty space has a non-zero value. There's some energy there, which is why when you have more energy that you try to flow through that, you end up seeing a particle. Basically, that's what it means, right? You could think of it as a lake, and the lake is pretty quiet, pretty flat, nothing there. Maybe a little ripples on the top, okay? And now you just take a giant rock and drop it in there. Well, that's gonna create waves, right? Well, if someone down the road dropped another rock and that created a wave, and those two waves met, and there's a disturbance pattern there and they overlap, that's what you and I would perceive as a particle. But one of the most basic things about this is that, for instance, just take mass. I'll end it off on this. Just take mass. The proton, we said, has most of the mass. You get 1% from the Higgs, and then your strong nuclear force gives you most of the rest of the mass of the atom. But something like a WZ boson has billions of electron volts worth of energy. So how do you explain that? How do you explain empty space having more energy than a proton? And that's difficult to explain. But that's why quantum mechanics is so crucial to truly understanding general relativity. I believe they do coincide. I'm not an expert, so I don't know exactly where the problem is, you know, in terms of like understanding. I think it's gravity is what it boils down to. They don't have a way to quantize gravity. There's nothing substantive that we can grab onto. There's nothing we can point to say, aha, that particle is responsible for gravity. So it's one of the only forces, although it's not a force, that doesn't have a good explanation insofar as they can't find a disturbance pattern, they can't find a particle. What they can find though, okay, with the LIGOS is they have this thing called a DeWitt experiment where they use two lasers, okay, and they point them in such a way that when gravitational wave comes through, they can pick up on it. And so they've actually proved, as of recently, that gravitational waves are indeed real. They knew they were real anyway, but now they can prove it with this equipment at LIGOS. But anyway, I hope you liked the video. We're going to get into black holes and things like that. We're also going to link this with modern adult hygiene and cognitive health. So we're going to blend that together and hopefully come out something that you guys will like.